Zener diodes. These diodes are also known as breakdown diodes. These are semiconductor devices. These are PN junction devices. They require reverse biasing for their operation. Structurally, they exhibit certain differences from the structure of ordinary diodes. The impurity concentrations, P side and N side, these are high in Zener diodes when compared to impurity concentrations in ordinary diodes. As a result, the junction width in Zener diodes is also small, very small when compared to junction width in case of ordinary diodes. When it comes to behavior, Zener diodes behavior under reverse bias is almost same as that of ordinary diode until the bias voltage reaches certain point. Below this voltage, Zener diode, ordinary diode both flow very little amount of current. This current is known as reverse saturation current. It is so small, usually one can neglect it. In case of Zener diodes, when bias voltage reaches a point, this point is called Zener voltage or breakdown voltage. The diode starts conducting abnormal amount of currents, huge amount of currents. This is one aspect from which Zener diodes differ from ordinary diodes. Another aspect worth noting about Zener diodes behavior is that beyond Zener voltage, even a small change in the bias voltage causes huge change in the current that is flowing through the diode. This property is quite useful. It finds applications in several areas like in the design of voltage regulators, in the design of double clippers or amplitude limiters, in the design of meter protection circuits, and also in several other areas. Special diodes, Zener diodes, series on semiconductor devices and circuits, lecture number 2.21. Zener diodes or semiconductor diodes, PN junction diodes, They belong to the category of special diodes. Diodes are broadly put into two categories. Ordinary diodes, which are used mainly for rectification, clipping, clamping, etc., and special diodes, which are used for special purposes. Diodes like Zener diodes, varactor diodes, tunnel diodes, these are all fall in the category of special diodes. In the present session, we focus on Zener diodes, their structural features, constructional details, their current voltage characteristics, and also their applications. Now, let us move further to begin the session. A few introductory points are given here. Zener diodes are also called avalanche or breakdown diodes. Under reverse bias, junction diodes start flowing huge current when voltage is beyond certain value called breakdown voltage, Zener knee voltage, Zener voltage, avalanche point, peak inverse voltage. All these terms refer to same and one voltage. Usually it is called breakdown voltage. There diodes also exhibit large current variation for small voltage changes. This characteristic is useful in several situations like regulation, clipping, etc. Notice for clipping, for clamping, ordinary diodes can be used. Zener diodes also can be of much use, good use. Regulation, when it comes to voltage regulation, ordinary diodes, they don't work. We have to go for Zener diodes. Now, some more points. Ordinary diodes cannot withstand these currents and voltages and get permanently damaged. If we try to operate an ordinary diode at or beyond breakdown voltage, it cannot withstand such high voltages and such high currents, resulting in a permanent damage, even burnout of the diode. That is the case with ordinary diodes. But when you use the Zener diodes, they are designed, they are fabricated, they are made with such materials that they can withstand those high voltages and high currents. That's what he's telling. Zener diodes are designed with adequate power dissipation capabilities because their design is such. The materials that are used in their design, they are such. So they can withstand high voltages and currents. They can also have the capability of power dissipation, high power dissipation. So we can operate them in the reverse breakdown region. Silicon is widely used for their construction to make use of its capability to handle higher currents and temperatures and also higher heat dissipation capabilities. Silicon semiconductor, it is associated with these properties: capability to handle higher currents, capability to withstand higher temperatures, and it has even higher heat dissipation capability. These diodes use high doping concentration. Important features are being given here. First point says silicon is widely used material, about material. Second point says doping concentration is high. Another point regarding these diodes is depletion region width is very small. Depletion region is very thin, less than 1 micrometer. The electric field in the depletion region is very high, about 500 kilovolts per meter, even for a small reverse bias voltage of about 5 volts. Notice field is potential gradient. As width is small, potential gradient naturally becomes very high. The thin depletion region allows electrons to tunnel from the valency band of the p-type material to conduction band of the n-type material. Tunneling is a phenomena associated with the quantum mechanics. According to quantum mechanical principles, a particle need not have energy corresponding to the barrier height to cross it. Even when particle's energy is lower than barrier's energy, it can pass through the barrier to the other side. It can tunnel through the barrier. He is telling because of thin depletion region, tunneling phenomena becomes significant and electrons and holes cross from one side to another side, even though their energy is not sufficient to surmount the barrier. It is doped in such a way that it produces controlled reverse bias properties. The breakdown voltage is controlled by doping levels and their gradients. Another point, the breakdown voltage can be controlled quite accurately in the doping process. For commonly available breakdown diodes, it varies widely from 1.2 to 200 volts. It allows current to flow in the forward direction in the same manner as an ideal diode. So the point one has to keep in mind always is 1. Zener diode or breakdown diodes, they are operated in reverse biased direction. In the applications, they are always in the reverse direction. Out of curiosity, if we want to know how the diode behaves when it is forward biased, then here this point says in the forward direction its behavior is the same as an ordinary diode. Another point, in the atomic scale, this tunneling corresponds to transfer of valency band electrons into empty conduction band states due to reduced barrier between these bands and high electric fields that are induced due to higher levels of doping on both sides. Some more points which can give us an understanding, a deeper level of understanding regarding the functioning of breakdown diodes. There are two mechanisms recognized for diode breakdown under reverse bias. One is called Zener breakdown, other one is called avalanche multiplication. In Zener breakdown, what happens? The strong force due to the applied field tears away the valence electrons from the covalent bonds in the junction region, creating electron hole pairs and consequently large current. In avalanche multiplication, another phenomena, highly energetic charged particles after colliding with the crystal ions gain sufficient energy to disrupt the covalent bonds, thereby generating more and more electron hole pairs. The newly generated carriers further participate in the disruption process, increasing carrier concentration in a cumulative manner and hence large current. There are two possibilities for the functioning, for the behavior of Zener diodes or breakdown diodes. One possibility is Zener breakdown, another possibility is avalanche multiplication. Of course, both do not happen simultaneously. Only one happens in any diode. Zener breakdown, it is due to field ionization. It is the field which creates carriers. High level or high intensity field which generates electron hole pairs. So Zener breakdown is due to field ionization. Second one, avalanche multiplication. It is due to collisions. Due to collisions, multiplication of the carriers happen, and suddenly the carrier concentration rises and current consequently rises. So it is avalanche. Rise is an avalanche kind of thing. Both types of phenomena occur under reverse bias, with the Zener effect predominating under 5.6 volts and avalanche breakdown above this voltage. So above 5.6 volts, it is avalanche breakdown. Below, it is Zener breakdown. So Zener breakdown happens at lower voltages when compared to avalanche breakdown. These two mechanisms, avalanche breakdown, Zener breakdown, both are compared here. Avalanche breakdown is due to impact ionization, collisions. Zener breakdown is due to field, higher levels of the field. Avalanche breakdown is associated with carrier collisions with ions, as already mentioned. Here, no carrier collisions. Avalanche breakdown happens when the doping is light. When it is heavy, Zener breakdown. Note that here light doesn't mean lighter when compared to ordinary doping levels. No. In avalanche as well as Zener breakdown diodes, doping is high, doping is heavy. Here light means when compared to doping level in Zener diodes, in case of Zener breakdown. Similarly, in avalanche breakdown, the diode depletion layer, you can find it broader when compared to the diode when it is carrying Zener breakdown. So avalanche breakdown means broader depletion layer, Zener breakdown means narrow depletion region. Temperature quotient of voltage is positive in case of avalanche breakdown. Temperature quotient of voltage is negative in case of Zener breakdown. A typical figure of voltage gradient field intensity in the junction region is given here. It is 2 into 10 power 5 volts per cm in case of avalanche breakdown. It is 2 into 10 power 7 volts per cm in case of Zener breakdown. Usually breakdown voltage is more than or equal to 5 volts. In case of avalanche, it is less than 5 volts. In case of Zener breakdown, as already mentioned. VI characteristics of Zener diodes or breakdown diodes are shown here. So this is the symbol. First of all, we should know the symbol. This is the symbol of ordinary diode. Here Z is superimposed over the symbol of ordinary diode, Z indicating Zener, Z standing for Zener. In B is shown a Zener diode. It is working as a regulator. What is a regulator? In this application, Zener diode to some extent controls voltage variations across load. The voltage variation may be due to variation in V, source voltage, or it may be due to change in R. In either case, the Zener diode tries to maintain Vz a constant. Here it is told application of Zener diode to regulate voltage across the load against changes due to variation in load current. Suppose RL is varied, then naturally voltage. In the absence of Zener diode, voltage across RL changes. But when we place Zener diode across RL, the change in the voltage across RL, load voltage, that change is to some extent it is arrested, prevented. When supply voltage changes, in that case also load voltage changes. But this change, it is reduced by the presence of Zener diode. It is called regulation, voltage regulation. Now let us spend some time on volt ampere characteristics of Zener diode. On forward biased side, its characteristic is very much similar to an ordinary diode. Up to certain point, current is zero in the forward direction. After that, current starts increasing with voltage in an exponential manner, which is same as an ordinary or any ordinary PN junction diode. In the reverse direction, reverse biased condition, the current in the diode is almost zero until voltage reaches certain point called Vz. Actually, current starts increasing when voltage reaches a level, we can call it Vzk. Up to Vzk, current is insignificant, negligible. When voltage is Vzk, current starts rising. The rise is tremendous. That is the point one has to understand. Small increase in voltage in reverse direction, it is causing a huge rise in its current. Here a voltage Vz, a current Iz are indicated. Vz, Iz. Actually Vz, Iz stands for the operating point of the diode. It is operated here at this point. Here equivalent circuit of a Zener diode, it is being given here. This is actual Vi characteristic. This can be approximated by a characteristic that is shown in B. Positive side, a voltage V gamma is cut in voltage. The characteristic is rising steeply at V gamma. On the negative side, the characteristic is falling in a straight line manner at a voltage Vz. Approximating the characteristic like this, as shown in B, it is called piecewise linear model. Actually, the current rise is exponential on the forward side. Reverse side, it is not straight fall. It is falling steeply, but it is not straight. But this fall is approximated by a straight line. The rise, which is exponential, it is also approximated by a straight line. So this is an approximation to make the calculations simple. This particular approximation is resorted to. So first piecewise linear model, and from that equivalent circuit. This is equivalent circuit. This is in one equivalent circuit of the diode when it is working on or under forward biased condition. In 2 is equivalent circuit of the diode when it is under reverse bias, but reverse bias voltage is less than Vz. When it is working under reverse bias at voltage Vz, then 3 gives the equivalent circuit. So first one is equivalent circuit under forward biased condition. Second one is equivalent circuit under reverse biased condition, but reverse biased voltage is less than Vz. When it is working at Vz, third one is the equivalent circuit. D, one can find the functioning of Zener diode as a regulator, which is already explained. Applications, several applications are there. Here we mention one after another. Main purpose, main use of Zener diodes is voltage regulation. These diodes are capable of regulating the load voltage against variations in load current or in supply voltage. Meter protection. A Zener diode, when connected in shunt, can protect a meter movement or circuit against damage from an accidental application of excessive voltage. So voltage regulation, meter protection. Zener diodes are also used for clipping off the input waveform in wave shaping circuits. So clippers, in the design of clippers also can be used. Switching operation. Zener diode can produce a sudden change from low current to high current. The use of Zener diode switching operations has made possible an extremely fast performance in computer applications. So they can be used as switches in the design of gates. They are also used as voltage reference. These are used as voltage reference under reverse biased conditions. When voltage references that need to be highly stable over long periods of time is required, a Zener diode with a temperature quotient of +2 millivolts per degree centigrade with a background voltage of 6.2 to 6.3 volts is connected in series with a forward biased silicon diode manufactured on the same chip. The FB diode has a temperature quotient of -2 millivolts per degree centigrade, causing the temperature quotients to cancel out. When a high voltage reference is required, two or more diodes in series rather than a single diode are used. This combination allows higher voltages, higher dissipation, lower temperature quotient, and lower dynamic resistance. With this, we come to the end of this session on Zener diodes. Before closing the session, let us recollect the important aspects we discussed in the session. Zener diode has been introduced, its properties are described, its structural features are given, materials used for their fabrication, they are mentioned. Current voltage characteristics of Zener diodes are given. Equivalent circuits of Zener diodes, they are also given. Applications are given just before the end of the session. Hope this session is useful to you. We meet again in another session with a new topic soon.